Okay, so next up we have Garie to talk about breaks and links.
Okay, thank you to my supervisor, Dr. Ng Kising, and greetings to my supervisor, Dr. Ng Kising, and my examiner, uh, Dr. Majajin, and also audience. So my name is Garie Tankajin, and today I want to give a presentation on my final year project, an introduction to break and links. So the main goal of this presentation is to actually study the link, equivalence of link by using a different perspective. So we have two kinds of perspective, which is the subset as of R3 and the closure of braids. So we also need to have some discussion on the braids. So let's now go into the discussion. So the first one we want to define is the abstract braid group, which is using by this abstract definition. So for positive integer n, the braid group Bn have n minus 1 generator. Then they satisfy two relation, which is for all I and j, they are satisfying in this set. The difference are greater than or equal to 2, then sigma j sigma I is equal to sigma I sigma j. And for I in this set, sigma I plus 1 sigma I will equals to sigma I plus 1 sigma I sigma I plus 1. So if it is not clear, it's fine. Later we will go back into this definition. Okay, so now we want to view this braid geometrically. So the geometric view we use is called braid diagram. So I will also use a example to go through this definition. So why is this braid diagram? Because this one is R, this one is I, which is close interval 0, 1. Okay, then as you can see, these strings are disjoint, and the point, the starting point, which is at the t equals to 0, which is 1, 0, 2, 0, and 3, 0, and the ending point 1, 0, 2, 1, 1, 2, 1, and 3, 1 are unique for each string. So this just means that they do not start, we don't have two strings starting from a same point or ending on the same point. Okay, and then at this intersection point, they meet transversely. What does it mean by transversely? It's exactly like this, but the negation of this transversely is like we might have something like this. Okay, tangentially. Okay. Then, okay, so for each point in this plane, they belong to at most two strings. This just means that, for example, at here, no string. At here, those points belongs to one string. But at here, exactly this point and this point, they belongs to two strings. At here, it is green string and the red string, and the below it is blue string and green string. Okay, and then at this kind of intersection point, we call it a crossing, and we will distinguish whether which one is overgoing and undergoing, where I will define later. So as you can see, this red string is starting from 1, 0. So we call it first string. So this blue, we call it second, and the third, we call it, the green, we call it third string. Okay. Then now, what does it mean by this overgoing and undergoing? So it just means that in this crossing of braid diagrams, the crossing with no gap is above the other, is said to be overgoing. And then the undergoing string is represented by a gap at the crossing. So just looking at this example again, we can see that this green string with no gap, this means that this green string is above the red string. Therefore, we say the green string is overgoing at this crossing. The red is undergoing. So at this another crossing, the blue one is now overgoing, but the green is now undergoing. Then now we define the isotopy of braid diagram. This just means that if we are given these two D and D prime, they are isotopic. If I have a continuous map, such that I can map one to another. But notice that we have a T. We have a T at here. So for this T in this I, which is the 0, 1, we need that for each T, the map is continuous. Then we call this whole family of braid diagram that we map from this function isotopy of D into D prime. Okay, so for example, this one is T equals to 0. This one is T equal to 1. So maybe at this T equals to 0.5, I may have something like this. Depends on how I define. Maybe at here. Okay. And now let's continue. So the operation of this Braids diagram is a product. So we are given, let's say that we are given D1 and D2. The product D1, D2, which is not commutative, is that I first place D2 at the bottom and D1 on the top. And I rescale it such that this is T equals to 1 and this is T equals to 0. Okay, if I do not rescale it in my, if for two product, it might have become T equals 2, which violate the definition of the Braids diagram. Okay, so also as this D1, D2, the order actually is from the first one is here and then the second one is here. So which means we follow the order of the composition of function, which we do G first, then we do F. Okay. Then now let's look at one example. So let's say that we are given this D1 and D2. If I want the product D1, D2, I put this braid at top, but now it is T equals to 2. Then I rescale it down. Then I will get a diagram like this. Okay, so let me draw a line at here. You can see that this is D2 and this is D1. And T equal to 1, T equals 0 is good. Okay, now continue. So now we will define the braid move, which will have an important role when we want to study the equivalence of links. So braid move consists of level preserving and boundary preserving isotopy. What does this level preserving and boundary preserving means? For example, I draw a line, a braid like this. Sorry. Like this. I cannot map it into something like this because the overgoing and undergoing data already changed. So it's not level preserving. Also, I cannot map it into something like this because for the first string at here, ending here, but now it ends at here, which is 1, 1. I changed the boundary, so it's not boundary preserving. Okay, then and three local changes. What are the local changes? I cross this full string like this. This is the isotopy we see just now. So I move this crossing above or below. And then I pull this middle string because why I call this middle string? Because it's undergoing at once, overgoing once. So it's middle string. I can pull it like this or I can pull it like this. Okay. We will see very similar thing, maybe exactly the same thing later in the randomized moves. Okay. So this set of Braids diagram is actually a group. Therefore, we identify it with the abstract Braids group. What does this mean? So this just means that when we are given the Braids diagram, I can write it as a product of Braids generator and vice versa. Okay. So how do I do that? I define on this generator, I define it as this Braids diagram, such that sigma I is the I shown as the overgoing shown and cross with this I plus 1. So for the I sigma I minus 1, I shown as the undergoing strain and cross with this I plus 1 strain. Okay. Then looking at this example again, if I draw a line like this, we can see that this is actually a sigma 2. This is a sigma 1 inverse because of we're looking at this. Now we look at this as the first, second, and third. Okay. Therefore, this is the first strain which is undergoing and cross with second. This is a second strain, overgoing, cross with third strain. Therefore, I can actually write this D1 as sigma 1 inverse sigma 2. So I can, if I give a sigma 1 inverse sigma 2, I can draw it back to this D1 also. Okay. Then now we want to go into links. So links is just a disjoint embedding n copies of n1 to R3. Okay, we just look at the diagram. So for example, this one is one circle, one copy of circle. This one is one copy of circle, but this one is two copy of circle. When we have only one copy, we call it a knot. Okay, as this have two copy, I call it a two component link. Okay, then continue. If there is a n component unlinked, then just means that the boundary of them disjoint. So if I want 4 component unlinked, I draw one more. Okay. Then now the ambient isotopy of link. We want to define this because this is the equivalence and equivalence relation on this link. Okay, so this L isotopic to L prime, if I can continuously deform, which is very similar to the definition of isotopic of braid diagrams. So, but here we have homomorphisms. Okay. Then, for example, if I'm given a link like this, the ambient isotopic will have something like this. These two are said to be ambient isotopic, which is similar to what we say we treat the strain, the line having elasticity. Okay. Then now I actually want to map this link diagram into a subset of R2 because previously those diagrams are in R2. Okay, so we want to find a way that we can map it into R2 and does not lose the information of the link. Okay, then I first introduce this multiple point. Look at our best friend of link. Okay, what is the multiple point? This and this is the multiple point. Because when I map to z equals to 0, I have multiple points that mapping into the same point. Okay, then a projection of a link is said to be regular. Looking at this example again, if each multiple point contains exactly 2 points, so this 2 exactly 2 points, the top straight and the bottom straight, right? And then there are finally many crossing. In a braid diagram, we also call, sorry, not braid diagram first. This one and this one we also call the crossing. Okay, so you can see that we have only 2, which is finite, and then the 2 straight meet transversely, which is exactly like the one we defined in the braid diagram. Okay, then the link diagram is just the image of a regular projection of link. So I take a link, I do regular projection, and then this regular projection actually keep the overgoing and undergoing structure. So for example, at here, this is overgoing, this is undergoing. So I know which strain is above and below. If a projection that do not preserve this data will be like something like this, then I do not preserve any data. I don't know which one is above, which one is below. Okay. Then now we define some move in order for us to introduce the important theorem, randomizer theorem. Okay. So the first one is planar isotopy. It's just a sequence of moves such that I can move this crossing like this, move this crossing like this. The length of the line can change, okay, with this planar isotopy. Then the randomizer move will consist of this planar isotopy that we defined just now and 3 local changes, which is very similar to what we see in the braid moves. The second and third, which is exactly seen in braid move. Then the first one is a little bit different. I twist the line or untwist the line. Okay. Then now this randomizer theorems tells me that 2 links are equivalent if and only if the link diagram that are representing them are related by a sequence of randomized moves. So now if I want to study these 2 links are equals or not, are equivalent or not, I can project them, look at the link diagram, and I find a sequence of moves, randomized moves. Okay. This will mark the end of a loop, view this link as a subset of R3. So before going into the link as closure of braid, we will introduce the orientation on the links. Okay, so just look at the example of link again. Oriented link means that I give orientation like this. Okay, so it's obvious that each component, since they are circle, I can have at most 2 orientation. I can assign 2 orientation. So for this isotopy, this oriented link, we also consider ambient isotopy. Therefore, when we say isotopy for link, we don't say the ambient word. Okay, I say isotopy, it means ambient isotopy. Then now, we start to look this link as closure of braid. So in this session, we will actually take the natural orientation of the braid. Let's say that I give you trivial braid. What is the natural orientation? This is t equals to 0, this is t equals to 1, right? Then the natural orientation is like this, from starting to ending, from starting to ending. Okay, then the standard closure of a braid beta with n string is that we identify the point I0 with I1. How do we identify it? So this one is 1, 0, 1, 1, identify. This one, identify. Then this one actually have the orientation. Okay. Then now we can see that every braid gives rise to a link. Let me draw one example. So identify a link, okay? But this is actually a knot because with only one component. Then now the Alexandria theorem tells us that every oriented link can represent as the standard closure of a braid. Let's say that I give you this Hoff link again. You can surely represent it as this beta. I don't know how many string that contains, but I can identify it and then I can represent it like that. Okay. Then by this theorem, we will naturally ask one question. Let's say that I'm given two standard closure of braid that are representing equivalent links. Does this imply that the braid of them are the same? But it is actually not. Why? Okay, looking at these two braid, they are different because these 2 and 1 are equals to 1, which is smaller than 2. Implies that sigma 2, sigma 1 do not equals to sigma 1, sigma 2. So beta 1 do not equals to beta 2. Okay, so these two are different braids. But looking at the standard closure of beta 1 and beta 2, immediately it seems that these two are different. But the difference actually can be related by a sequence of randomized moves. How do we relate that? So this crossing by a sequence of randomized moves, I can map it down so that I represent this beta 1 hat exactly to beta 2 hat. Oh, sorry, forget to mention this beta 1 hat stands for the standard closure of beta 1. Okay, so I now represent this as this. Then by random master theorem, it tells me that these two standard closure of braid must represent equivalence link. Then now we have an example such that different braids represent equivalence link. Then now we will want to introduce some move to fill in the gap such that a braid up to some move, then the standard closure of them represent as equivalence link. Okay. Then now first, if we define this standard, tensor product of braid. Given a beta and beta prime, the strain are not necessarily the same. Okay, then beta tensor beta prime is just placing this at the right. Okay, very straightforward. Then I can define this Markov move and I can write it in terms of this braid generator. So Markov move 1 is that beta beta prime is equals to beta prime beta. Then the second move is beta tensor adding one strain, and I cross at the below because the following the order of the composition of function, I cross at below. Then it will equals to this beta. Look at the diagram, it will be very clear. So Markov 1 just means that I can interchange these two. Okay. Then Markov 2 means that I add one string, cross at below. I can cross it by using two way. Of course, I can go in back. Okay. Then we actually can now introduce this Markov theorem after this Markov move. So these two braid diagram, beta and beta prime, are representing equivalence if this beta and beta prime are related by a sequence of braid moves, which we define in the discussion of braid and the Markov move. So now to study this equivalence of oriented link, I just need to look at representing a standard closure. I look at the braid because a standard closure is always like this. So I can just look at this section and then whether these two braid are related by this braid move and Markov move. Okay, then now we want to go into the link as the plate closure of braids. Oh, never mind. One example. This is the example just now actually. So if I define beta equals to sigma 2 and beta prime equals to sigma 1, then these two are related by a sequence of Markov move. Then by the Markov theorem, these two must represent isotopic links. Okay, so we use different arguments. We can use different arguments. So now we go into the plate closure of braid. So in this section, we cannot consider the natural orientation of braid. I will tell you why later. Let's first define this plate closure of a braid. So it must be a braid with 2n string. It will be, the notation is a beta tilde. Okay. Then looking at the diagram, I identify the braid like this. First one is the odd one. I identify with it with the even. Similar at the t equals to 0 and t equals to 1. So I do it at t equals 0 and t equals to 1. Then like this, 1, 2, 2, 3, 1, 2, 3, 4, 5, 6, and then 2n minus 1, 2n. Then this one I will call it first bottom bridge, and this one I will call it n bottom bridge. Similarly, first top bridge and top bridge. Okay. Then why we cannot consider the natural orientation? Because let's say that I give you this trivial braid with 2 string. I identify it. If I consider the orientation, we can see the orientation clash. Okay. Then now, similar to the Alexandria theorem, we also have this airy link can represent as the plate closure of braid. Why is that? Because if we forget the orientation in the Alexandria theorem, airy link will represent it as a center closure. Then by a sequence of random isomorph, I can actually represent this center closure as this plate closure. Therefore, now I can represent this L as a beta tubular. Then this shows that every link can represent as a plate closure of the braid. Then now, we also want to define some move for us to fill in the gaps. Okay, so the bridge move consists of 3 moves. So the first move is to twist the bridge. Second and third both are changing the order of the bridge, but the second one is directly on top or directly on bottom, and the third one is in between. Okay, so actually we can see that this is a sequence of randomized move 1, which apply on the region that contains the bridge, and the second and third one are both a sequence of the randomized move 2. What is randomized move 2? It's this, and then I do something like this. Okay, so I just cross between. Then actually we have one more ways to apply this randomized move 1. We apply it on a region that does not contain this bridge. Then we can, if I twist this part, I will get something like this. And I call this stabilization. Going back, I call this stabilization. Okay, but you might wonder, how about the randomizer move 2 in the braid and the randomizer move 3 in braid or in the bridge? But actually we have no more move because randomizer move 2 and 3 on the neighborhood that does not contain the braid. It just exactly the braid move can do those things already. Okay, and then for the randomizer move 3, if you want to apply it on a region that contains the bridge, we cannot do it because randomizer move 3 contains 3 strain, but at the bridge you don't even have crossing. Okay. Then now we can finally define this Markov theorem for plate closure of braid. Given 2 plate closure of braid, P and P prime, they are representing isotopic link if they are related by a finite sequence of braid move, bridge move, stabilization, and destabilization. So for now, we can actually study the equivalence of link by looking at the plate closure of braid and check that whether they are related by those moves. So in conclusion, we study the equivalence of link by using those perspectives. So I consider the second and the third one the same perspective as they are both represented as the braid, closure as a braid. So the first one is subset of R3. So it's by random method theorem, it tells me that if I want to study the equivalence of link, I study the link diagram modulus out this random method move. For the second one, link as standard closure of braid, Markov theorem tells me that to study the oriented link equivalence, I can study the braid diagrams, modular out this braid move and Markov move. And the third one, plate as closure of braids. The Markov theorem for plate closure of braid tells me that I look at the plate closure and then I modulus out this braid move, bridge move, and stabilization and destabilization. This shows that the importance of this, the role of this braid in this link equivalence, which we can see that they are both closely related. And this will mark the end of my presentation, and thank you for listening.
Okay, thanks, Gary, for the talk. Does Jiajing have any question?
So you right. So nice talk, and you have mentioned that the main thing is that you can have, say, determine whether two links or two braids or oriented links, whether they are isotopic or not, by saying that you can mute 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 these two links by a certain step of moves. So do you have like a goal algorithm to get these moves? Say I give you two links, then you can produce a move which move the
Actually, this is
one link
actually
to another one.
quite the main problem by if we want to study the equivalence link by using those theorem. That's why we actually introduced the John's polynomial and Kaufman's polynomial to help us to have a way to determine whether they are the same. And because we only know that we can only look into those moves, but we don't actually have a algorithm. We know that they exist. If these two links isotopic, I given these two links isotopic, but I cannot find a sequence, then it's actually also a problem. But I cannot find this sequence doesn't mean they are not isotopic. So this is actually a problem in here. So for me, personally, the research I've done, I see no effective algorithm on determining this sequence of moves actually. Yes.
Okay, okay. So there's no algorithm, basically. The
Yeah, no
answer, short
algorithm.
answer is there's no algorithm.
Yeah, there's no
That's
algorithm.
weird.
Yes, that's very weird because this is actually
Maybe
I
even
seen through the argument.
non-effective algorithms. There's also no non-effective algorithms.
Yeah,
Like you
no, yeah. Probably algorithm, but not very effective also.
okay,
Yes.
okay, thanks.
Any more question for Gary?
Yongyan, you have question?
Young Young got question or not?
I don't have question.
Okay, so if no question, thanks Gary. So if there's any comment from Jia Jun, please correct in your thesis.
Okay.
Okay, thank you everyone for coming.
Bye bye.
Bye bye.
Nice
Thank you.
Okay, thank you.
Thank you, sir.
Bye bye.